Hello everyone, welcome to today's lecture. In today's lecture, we will practice some questions based on continuity and differentiability theory portions. And the questions will be from NCERT section 5.2, example 7 to 15. So let us start. The images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So, in this lecture, we will study example 7 to 15. So, let us start with the example 7. It says, is the function defined by fx is equal to absolute value of x a continuous function, right? We have a function given as fx is equal to absolute value of x, and it is asked that the given function is continuous function or not, right? So how can we find that the given function is continuous or not? What can we do? See, we will start solving this by using graphical method also, or by using limit method also, right? By using graphical method, what can we do? We will draw the graph of y is equal to absolute value of x, right? And we will see whether the graph is continuous or not, right? Whether we have to lift the pen while drawing the graph or not, right? And if we have to lift the pen, then the function will be discontinuous at the point at which we are lifting the pen, and it will be continuous if there is no point where we are lifting the pen, right? And for the analytical purpose, what can we do? We will try to define limit extending to a, when extending to, limit extending to a minus and limit extending to a plus, and the value of limit at x equal to a, right? So if all the three limits, the value of all the three, limit at extending to x minus, limit extending to x plus, and the value of the function at x equal to a will be equal, then we can say that the function is continuous, otherwise function is discontinuous, right? Okay, so in this way you can try to approach this question. Okay, so let us move to the solution part. So what can we do? We may write f as fx is equal to minus x if x is less than 0, and x if x is greater than equal to 0, right? Fx will be minus x if x is less than 0, and fx will be equal to x if x is greater than equal to 0, right? Now we know that the function f is continuous at x equal to 0. Let c be real number such that c less than 0, then fc should be equal to minus of c, right? Fc should be equal to minus of c. Clear? Also, limit extending to c fx, limit extending to c fx will be equal to limit extending to c minus of x, right? Why it is minus of limit extending to c minus of x will be equal to minus c. Why it is minus c? Because when we will put the value of c here, we will get minus of c, isn't it? Since limit extending to c fx is equal to fc, f is continuous at all negative real numbers, right? F will be continuous at all the negative real numbers, isn't it? Now, let c be the real number such that fc greater than 0, right? Then fc will be equal to c. Also, let limit extending to c fx will be limit extending to c x, and when we will put x as c, it will be c, right? Since limit extending to c fx will be equal to fc, f is continuous at all the positive real numbers, right? Hence, we have proved that the function f is continuous at all the negative values, that is c less than 0, and for also for also c greater than 0, it is continuous. Therefore we can say that the function f is continuous at all the points. Got it? And also we can draw the graph of the function fx, y is equal to absolute value of x, and this will be basically the graph of the function, right? This will be basically the graph of the function, straight line. So you can say that we need not to lift up the pen while drawing the graph, right? Clear? So in this way, we can say that the function y is equal to absolute value of x is continuous at all the points. Got it? Okay, let us move to the next example, right? Next example is discuss the continuity of the function f, which is given by fx is equal to x cube minus x square minus 1, right? We have to discuss the continuity of the given function f, which is given by fx is equal to x cube plus x square minus 1, right? It is example 8. Okay, so how can we draw, like how can we say whether the given function is continuous or not? So the hint of the given example is we again try to make the limit, right? When limit c less than 0, when c less than 0, limit extending to c will be equal to, we will put the value of c, and we will find whether when c less than 0, when c greater than 0, and the value of function at x equal to c is equal or not. If it is equal, then we can say that the given function is continuous, and if it is not equal, we can say that the given function is discontinuous. Got it? Okay, let us move to the solution part. Clearly f is defined at every real number c, right, and its value at c. What will be fc? The value of function at x equal to c will be c cube plus c square minus 1, right? It will be c cube plus c square minus 1, right? Now we also know that limit extending to c fx will be equal to limit extending to c x cube plus x square minus 1, which will be c cube plus c square minus 1, right? Thus, we can say that limit extending to c fx will be equal to fc, right? Limit extending to c fx will be equal to fc, right? Hence, f is continuous at every real number, right? We can say that the function f is continuous at every real number. Got it? This means that f is continuous function, right? F is the function defined by fx is equal to x cube plus x square minus 1 is continuous at every real number. That means function f is continuous. We can say that, right? Okay, let us move to the next question, next example. It is example 9, right? NCERT section 5.2, example 9. And it says that discuss the continuity of the function f defined by fx is equal to 1 by x when x is not equal to 0, right? The function defined by fx is equal to 1 by x when x not equal to 0, and we have to discuss the continuity of the given function, right? So how can we define the continuity of the given function? So we will try to define the functional value of f at x equal to c, limit of the function when x tending to c, right? And if it is equal, then we can say that the function is continuous, right, throughout. Okay, so let us see the solution part. Right? Fix any non-zero real number c. Let us fix any non-zero real number c. So we have limit extending to c fx will be equal to limit extending to c 1 by x, which will be equal to 1 by c, right? Which will be equal to 1 by c. Got it? Now, since for c not equal to 0, fc is equal to 1 by c, right? C not equal to 0, fc will be equal to 1 by c. We have limit extending to c fx will be equal to f of c, right? We have limit extending to c fx will be equal to f of c, right? And hence f is continuous at every point in the domain of f, right? F will be continuous at every point in the domain of f. Got it? So therefore we can say that easily f is continuous function, right? Right, f is continuous function. Got it? Since fx is not defined at x equal to 0, so fx is continuous except x equal to 0, right? Except x equal to 0, and it is defined that x not equal to 0, right? If it would not be defined that x not equal to 0, then we can say that the function will not be continuous, right? But it is already defined that the value of x is not equal to 0. Got it? So we can say that the function f is continuous function. Okay, so we can say that the function f is continuous at every point in the domain of f, right? At every point in the domain of f. Got it? Okay. Okay, let us move to the next question. Let us move to the next example. This example says discuss the continuity of the function, given function, and the function given as fx is equal to x plus 2 if x is less than equal to 1, and fx equal to x minus 2 if x is greater than equal to 1, right? If x is greater than equal to 1, right? So we have to discuss the continuity of the given function, right? We have to discuss the continuity of the given function. Okay. So how can we discuss? Let us see the solution part. The function f is defined at all the points of the real line, right? The function f will be defined at all the points of the real line. Got it? Case 1, if c is less than 1, c is less than 1, then the value of fc will be equal to c plus 2, right? The value of fc will be equal to c plus 2. Therefore, limit extending to c, fx will be equal to limit extending to c, x plus 2, which is equal to c plus 2, right? Which is equal to c plus 2. Got it? Thus, f is continuous at all real numbers less than 1, right? F is continuous at all real numbers less than 1. Got it? Case 2, if c is greater than 1, then fc will be equal to, if c is greater than 1, then fc will be equal to c minus 2. Fc will be equal to c minus 2, right? Therefore, limit extending to c, fx will be equal to limit extending to c, x minus 2, right? And it will be equal to c minus 2, right? Which is equal to f of c, right? It is equal to c minus 2, which is equal to f of c. Therefore, limit extending to c, fx is equal to limit extending to c, x minus 2, and it will be equal to c minus 2, right? And it is equal to f of c, right? Thus, f is continuous at all the points when x is greater than 1, right? Therefore, we can say that the function f is continuous at all points when x is greater than 1, right? Okay. Okay. Now let us see the case 3 if c is equal to 1, right? If c is equal to 1, then the left hand limit of f at x equal to 1 is limit extending to minus 1, limit extending to 1 minus fx will be equal to limit extending to 1 minus x plus 2, and it will be equal to 1 plus 2, right? Which will be equal to 3, right? 1 plus 2 will be equal to 3, right? Hence, the right hand limit of f at x equal to 1 will be 1 is basically limit extending to 1 plus fx is equal to limit extending to 1 plus x minus 2 will be equal to 1 minus 2, and right, and which will be equal to minus 1, right? Since the left hand and the right hand limit of f at x equal to 1 do not coincide, then we can say that f is not continuous at x equal to 1, right? Because left hand limit and right hand limit at x equal to 1 do not coincide. Hence, we can say that the function f is not continuous, that is, it is discontinuous at x equal to 1, right? Okay. Hence, x equal to 1 is the only point of discontinuity of the function f, right? X equal to 1 is the only point of discontinuity of the function f. Got it? Okay, let us move to the next question. Example 10. Example 10 says, discuss the continuity of the function f defined by fx equal to x plus 2 if x is less than 0, and fx equal to minus of x plus 2 if x is greater than 0, right? Fx is given as x plus 2 if x is less than 0, and fx is given as minus of x plus 2 if x is greater than 0, right? So how can we define the continuity of the given function defined by this one, right? So again, we will try to find the functional value at some functional value at x equal to 0, limit extending to 0 minus the value of the function at extending to 0 minus, and the value of the function at extending to 0 plus, right? If all the limits will be equal, we can see that the given function is continuous. The given function is continuous. Okay. So let us see the solution part. The graph of the given function as shown in the figure 5.4, right? You can see the given function 5.4, right? So this is the graph, right? When x is less than 0, the value of function is defined as this one, right? And when x is greater than 0, the value of function is defined as this one, right? Got it? Okay. Okay, let us see the example 11. Find the point of discontinuity of the given function f defined by fx equal to x plus 2 if x is less than 1. It is 0 when x is equal to 1, and it is like greater than 1 when x is, it is will equal to x minus 2 if x is greater than 1, right? The function fx is defined as x plus 2 if x is less than 1. It is equal to 0 if x is equal to 1, and it is equal to x greater than it is equal to x minus 2 if x is greater than 1, right? Again, we have to basically find the like points of discontinuity of the given function. We will try to draw the graph of the given function, piecewise function, as well as we can try with the limits at limit extending to 0, limit extending to 1, limit extending to 1 minus, and limit extending to 1 plus, and the value of the function at x equal to 1, right? And if all the three limits will be equal, we can say that the x equal to 1 is the point of continuity, and if it will not be equal, then we can say that it is the point of discontinuity, right? Okay, we find that the function f is continuous at all the real numbers x not equal to 1, right? We find that the function f is basically continuous at all the real numbers when x is not equal to 1, right? The left hand limit of f at x equal to 1 will be, the left hand limit of f at x equal to 1 is limit extending to 1 minus fx is equal to limit extending to 1 minus x plus 2 will be equal to 1 plus 2, which is equal to 3, right? Which is equal to 3. Got it? The right hand limit of f at x equal to 1 is, what will be the right hand limit of f at x equal to 1 is limit extending to 1 plus fx is equal to limit extending to 1 plus x minus 2, and it will be equal to 1 minus 2, right? And which is equal to minus 1, right? Hence limit extending to 1 plus fx will be equal to minus of 1, right? Since the left hand and the right hand limits of f at x equal to 1 do not coincide, because left hand limit is coming out to be as 3 and right hand limit is coming out to be as minus 1, right? Since left hand limit and right hand limit do not coincide, we can see that f is not continuous at x equal to 1, right? The function f is not continuous at x equal to 1, right? Hence x equal to 1 is the only point of discontinuity of the function f, right? X equal to 1 is the only point of discontinuity of the function f. Got it? Right. Hence we can say that the function f is continuous at all the points except x equal to 1, right? Okay, let us move to the next question. And also for the previous question, example 11, we can see the graph of the function, right? See, the graph of the function is this one. We can say that function is discontinuous at x equal to 1, right? The function is basically discontinuous at x equal to 1, right? Okay. Okay, next one is example 12. Discuss the continuity of the function defined by fx equal to x plus 2 if x is less than 0, and minus x plus 2 if x is greater than 0, right? Fx is basically x plus 2 if x is less than 0, and fx is minus of x plus 2 if x is greater than 0, right? Let us see the solution part. Observe that the function is defined at all real numbers except 0. Observe that the function is defined at all real numbers except x equal to 0, right? So domain of the definition of this function is basically d1 union d2, where d1 is basically x belongs to real when x is less than 0, and d2 is basically d2 equal to x belongs to real when x is greater than 0, right? Let us see case 1. When c belongs to d1, then limit extending to c fx, limit extending to c fx will be equal to limit extending to c x plus 2, and it will be equal to c plus 2, right? Which is equal to fc, and hence f is continuous in the domain d1, right? Hence we can say that the function f is continuous in the domain d1, right? Let us take case 2. If c belongs to d2, then limit extending to c fx will be equal to limit extending to c fx will be equal to limit extending to c minus of x plus 2, which is equal to minus c plus 2, right, and which is equal to f of c, and hence f is continuous in the domain d2, right, f is continuous in the domain d2 as well. Since f is continuous at all points in the domain of f, we deduce that the function f is continuous, right? We can say that f is continuous at all points in the domain of f. We deduce that the function f is continuous. Okay. Right. Okay. See, we can draw the graph of the function as well. We can draw the graph of the function as well. When x is less than 0, it will be equal to x plus 2, and when x is greater than 0, the graph is this one, right? Clear? Hence, we can also say by using graph of the given function. Okay. Right. Okay, let us move to the next question. Note that the graph of the given function, we need to lift the pen from the figure 5.6 of the paper, right? But we need to do that only for those points where the function is not defined, right? Clear? Hence, f is continuous because at x equal to 0, the value of function is not defined, right? Okay, let us move to the next question, right? Next question is example 13. Example 13 says that discuss the continuity of the given function f where fx is equal to x if x is greater than equal to 0, and fx is equal to x square if x is less than 0, right? Fx is equal to x if x is greater than equal to 0, and fx is equal to x square if x is less than 0, right? So how can we define it? Let us see the solution part. Clearly the function is defined at every real number, right? Clearly we can say that the function is defined at every real number, right? So graph of the function is given in figure 5.7. See, we can draw the graph of the function fx is equal to x if x is greater than equal to 0, and fx is equal to x square when x is less than 0, right? Fx is equal to x square if x is less than 0. Got it? So by inspection, it seems prudent to partition the domain of definition of f into three distinct subsets of the real number, right? Three distinct subsets of the real number. Got it? Okay. So let domain d1 will be x belongs to real number when x is less than 0, and domain d2 is x equal to domain d2 is 0, and domain d3 is x belongs to real number when x is greater than 0, right? Now discuss the continuity. How can we discuss the continuity of the given function fx is equal to x if x is greater than equal to 0, and x square if x is less than 0? How can we define it? So let us see the solution part. Case 1, at any point in d1 we have fx equal to x square, and it is easy to see that it is continuous there, right? At x equal to fx equal to when fx equal to x square, it is easy to see that it is continuous there, right? Case 2, at any point in d3 we have fx equal to x, right? Fx equal to x, and it is easy to see that it is continuous there also, right? Case 3, now we analyze the function at x equal to 0, right? We can analyze the function at x equal to 0. The value of the function at 0 is f0 is equal to 0, right? Value of the given function, the value of the function at 0 is f0 is equal to 0, right? The left hand limit of f at x equal at 0 will be left hand limit of f at 0 will be equal to limit extending to 0 minus fx will be equal to limit extending to 0 minus x square, and it will be equal to 0 square, which is equal to 0, right? It is equal to 0 square, which is equal to 0. Got it? Now let us discuss the right hand limit of f at 0. Let us discuss the right hand limit of f at 0 is. So limit extending to 0 plus fx will be equal to limit extending to 0 plus x, which is equal to 0, right? Thus limit extending to 0 fx will be equal to 0, and it is equal to f0, and hence f is continuous at x equal to 0. We can say that the function f is continuous at x equal to 0, right? This means that f is continuous at every point in its domain, right? F is continuous at every point in its domain. Hence, we can say that the function f is continuous function, right? We can easily say that the function given function f is continuous, is a continuous function, right? Okay. Okay, let us move to the next question. Okay, our next example is example 14, and show that every polynomial function is continuous, right? We have to show that every polynomial function is continuous, right? How can we show that every polynomial function is continuous? So let us see the solution part. Recall that a function p is a polynomial function if it is defined by px is equal to a naught plus a1x plus a2x till an x to the power n for some natural number n when an not equal to 0 and ai belongs to R. Clearly, this function is defined for every real number, right? This function will be defined for every real number. Got it? For a fixed real number c, we have limit extending to c, px will be equal to pc, right? Limit extending to c, px will be equal to pc, right? So by definition, p is continuous at c, right? By definition, p is continuous at c. Got it? Since c is any real number, p is continuous at every real number, and hence p is a continuous function, right? Since c is any real number, p is continuous at every real number, and hence p is a continuous function. Got it? We can say that the function p is a continuous function. Okay. 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 Let us move to the example 15. It says find all the points of discontinuity of the greatest integer function defined by fx equal to greatest integer function of greatest integer function of x, where box x denotes the greatest integer less than or equal to x, right? Box x denotes greatest integer less than or equal to x. Got it? So how can we define? Let us see the solution part. First, observe that f is defined for all real numbers, right? Observe that f is defined for all the real numbers, right? So graph of the function is given in figure 5.8, right? You can see the figure 5.8, and a graph of the given function is this one, right? So the value of greatest integer function will be like when x is less than 0, when x is less than 1, it will be the value will be 0. Greatest integer function of x will be equal to 0. When x is less than 2, the value of greatest integer function will be 1. When x is less than 3, the value of greatest integer function is 2, and like that, right? Got it? When x is less than 0, the value of greatest integer function will be negative 1, right? When x is less than negative 1, the value of greatest integer function is negative 2, right? And like that. Okay. So you can easily observe that the function is discontinuous at every integers, right? The function is greatest integer function of x is basically discontinuous at every integers, right? From the graph, it looks like the function looks like that the f is discontinuous at every integral point, right? Clear? So case 1, let c be a real number which is not equal to any integer, right? Let c be a real number which is not equal to any integer. So it is evident from the graph that for all real numbers close to c, the value of the function is equal to greatest integer function of c, right? It is evident from the graph of the function that we have seen previously. For all real numbers close to c, the value of the function is equal to greatest integer function of c, right? That is limit extending to c, fx will be equal to limit extending to c, fx is equal to limit extending to c, greatest integer function of x, right? Which is equal to greatest integer function of c. Got it? Also, fc is equal to greatest integer function of c, right? Fc is equal to greatest integer function of c. Okay. Hence, the function is continuous at all the real numbers not equal to integers, right? Hence, we can say that the function is continuous at all the real numbers not equal to integers, right? Okay. So at every integral point, the value of the function will be discontinuous. Okay. Case 2, let c be an integer. When c will be an integer, then we can find the sufficiently small real number r greater than 0 such that greatest integer function of c minus r, which is equal to c minus 1, right? Whereas greatest integer function of c plus r will be equal to c, right? This in terms of limits means that limit extending to c minus fx will be equal to c minus 1, right? Limit extending to c minus fx will be equal to c minus 1, and limit extending to c plus fx will be equal to c. Now, since these limits cannot be equal to each other for any c, we can say that, and the function is discontinuous at every integral point, right? The function will be discontinuous at every integral point. Okay. Okay. Hope you understood all the examples that we have discussed, right? And hope you liked our lecture. Okay. Thank you so much.